In this video, I will talk about velocity, acceleration, and Newton's second law in a rotating frame of reference. So I'm using the same frames of reference as in my previous lecture. The blue one is the inertial frame of reference, the red one, that's my rotating frame of reference, and uppercase omega is my angular velocity, the angular velocity of the rotating frame of reference. Now, in an inertial frame of reference, the net force is equal to the second time derivative of the position vector, but this has to be done with respect to the inertial frame of reference. Now, what I want to do, I want to see how Newton's second law, what it looks like when I have the second time derivative, but with respect from a non-inertial frame of reference, from a rotating frame of reference. Of course, I do anticipate that there will be some mathematical terms I have to add here. Okay, so that's what I'm looking for. That's the goal of this work, to find what do I need to add here to bring Newton's second law into this form, where I'm differentiating not on the inertial frame of reference, but on the rotating frame of reference. Okay. Now I did show you last time that you can take a time derivative in inertial frame of reference, and this will be equal to the time derivative in the rotating frame of reference with the addition of this cross product. Now, what is this? This is the velocity, okay? This is the velocity, but from the inertial frame of reference. This here is the velocity from the rotating frame of reference, and the two are not simply equal to each other. There is a component you have to add because your rotating frame of reference is rotating. Now, to find the relationship between the acceleration in the inertial frame of reference and the acceleration of the rotating frame of reference, we need to take the time derivative of this one more time. Now, that work does get complicated, but at the end of the day, the second time derivative of position at the inertial frame of reference is equal to the second time derivative of the position vector with respect to time from the rotating frame of reference with the addition to omega cross dr dt, the linear velocity, plus the angular velocity cross product with the cross product of the angular velocity cross r. Okay, so this will give you a vector, and whatever vector you get here, you do one more cross product with the angular velocity. And this here is the acceleration from the inertial frame of reference. This here is the acceleration from the rotating frame of reference. And now this expression will allow me to make the transition from here, from Newton's second law in the inertial frame of reference, to what Newton's second law looks like in the rotating frame of reference. So this is gonna give me F net equals the mass times the second derivative of the acceleration plus the mass, say 2m omega cross r dot plus the mass times omega cross r. And once again, this is what Newton's second law looks like in a rotating frame of reference. Now I can rearrange it if you want. So I'm gonna leave mr double dot. This is the acceleration as measured in the rotating frame of reference. This is equal to the net force minus 2m, I'm bringing everything to the other side, cross r dot minus m omega cross r. Okay, so we are used to a mass times acceleration equals the net force, and we have that in the rotating frame of reference. But in addition to this, because our frame of reference is rotating, we also need to add those two terms. Are those two due to any real interactions? No, they're not. They are simply there because of our transformation from the inertial to the rotating frame of reference. There are no interactions involved here. When you apply Newton's second law in a rotating frame of reference, you will use all the interactions you know, you will find the net force, and then you will add these two terms as well if you want to accurately predict the motion or the acceleration of the object in your rotating frame of reference. Now, even though these two terms are not due to an interaction, it is important to remember the acceleration in the rotating frame of reference does depend on those two terms. You cannot neglect them because they are not due to any interaction. They do mathematically affect the acceleration that you see, that you measure in your rotating frame of reference. And for the last thing, the name that we use for this is the Coriolis force, and this one is the centrifugal. Alright, that's all the theory I had.